Hello and welcome to my math channel. This is my very first video on YouTube. In this video, I will talk about change and rate of change. So, what is change? We refer to change in a variable with respect to another variable. That means we imply that there is a correlation between the variables. For example, in the first graph, correlation between the variables x and y exists mostly for the positive values of x. The second graph, which is known as a sigmoid curve, is what we commonly call as a change. For example, it represents a voltage increasing from 0 volts to 1 volt over a period of time. Natural changes are always smooth and take time. This also applies for the rate of change and the derivative of any order. The third graph is the bell curve, also called the Gaussian curve, which resembles the derivative of the sigmoid curve. This curve also represents the natural distribution of randomness around a mean value. The last one is the 11th derivative of the bell curve, which starts to look like a sine curve modulated by an exponential function. This seems to tell us that the rates of change at higher orders for a natural process are actually oscillations or vibrations whose amplitude has a bell curve as the envelope. I find that pretty interesting. A small detour here. So, how do we perceive a change? Well, it requires the ability to perceive the state of something at two different time instants or spatial locations, and then compare them to determine the magnitude of difference between the states. Also, we can confirm that the time and change do not exist independent of each other because they define each other. Now let's look at some basic types of change. The first one is the exponential change. This happens when the change is aware of the previous output or the subject which is undergoing the change. For example, the population growth. In general, such awareness involves a multiplication operation. Linear change does not reflect such awareness. It's a constant change, so it is linearly dependent on the number of iterations or the variable x. The lack of awareness of the subject is a characteristic of addition or summative operations. Polynomial change happens through accumulations of linear change. Here, the second level is a quadratic change and the third one is a cubic change. Here, the exponential change is contrasted with the linear change. On the left, we have a water tank where the rate of water being drawn out is dependent on the pressure of the water at the bottom of the tank, which in turn depends on the volume of the water, which again is being changed by the outflow. Due to this awareness or connectedness between the quantity and its change, the rate of change is exponential. On the right, water is being pumped out at a constant rate, which lacks that awareness or connectedness between the change and the subject. So this change is linear. This curve shows us the beauty of exponential change. The change in the radius of this curve is well connected to the radius itself. This is an equiangular curve, also called as logarithmic curve. The exponential change at discrete intervals through recurrence can also cause self-similarity or fractalness. Here, this fractal curve is produced by the simple expression as shown here, that is x plus a by x minus a. Another kind of change is where the derivatives are cyclic. That is, as we differentiate a function again and again, we cycle back into the original function after a few iterations. Here in this picture, we see that the magnitudes of the sine and cos functions are also the rates of change in each other. That is, if we ignore the sign. The recurrent changes lead to cyclic changes on the Riemann sphere. Here I define something which I call as a third inverse, which I'm sure there might already exist some formal name for it. This is minus 1 by x. I think this completes this set of basic arithmetic operations in the complex plane when projected onto the Riemann sphere. The quarter cycles are interesting. For example, the change from plus x to minus x goes through ix on its way. There is so much beautiful and symmetric stuff going on in this diagram here. Now let's utilize what we have learned to understand the real beauty of the exponential function. On the left is what we have already seen, the exponential curve in polar coordinates. The curve in the middle is called loxodrome. This is similar to the first curve. While the first curve intersects the radial lines at the same angle, the second curve intersects the meridians or the longitudes at the same angle. The points of infinity and 0 occupy the poles of the sphere. This is how the exponential curve looks on the Riemann sphere. On the right, we can see that the exponential curve still has some symmetry in its general form in the Cartesian coordinates. Both sigmoid and bell curve approach the e to the power x when the change is infinite. Here is a beautiful representation of a geometric series as a symmetric system arising out of partitioning the range 0 to 1 into two parts. Since the geometric series involves multiplying the current term with a factor, the change is subject aware. So it is related to an exponential change. We'll use this geometric series in the construction of the exponential curve in the next slide. Of course, e to the power minus x is equally beautiful. What we see here is a geometric construction of the exponential curve through a close relationship of the curve with a sloping straight line. We'll use complex numbers in exploring the exponential functions further in the next few slides. Here I have added a few diagrams to introduce the complex plane and its transformations through a few simple functions or mappings. I have used the great JavaScript tool by David Bow to create these diagrams. The complex domain brings a cyclic nature to the exponential curve on one of the axes. The exponential function is a cyclic periodic on the imaginary axis. There are multiple paths to arrive at e to the power x. We'll explore a few of them. This one uses a standard definition for e to the power x using the limit. However, we consider a finite value for n and see how the function evolves into e to the power x as n increases. The edge of the polynomial circle becomes a straight line to transform into the exponential function. Here we arrive at e to the power x from a sigmoid function. By reducing 1 in the denominator to 0, we can see that the sigmoid approaches the exponential. Here is one more standard definition of the exponential function using factorials and the sum of infinite series. Again, we start with a finite number of terms in the series and we see it approach e to the power x as the number of terms increase. This is an interesting sum of trigonometric values which are superimposed to become e to the power ix. This happens because the upper parts of the trigonometric functions mostly cancel out each other while lower parts of the functions reinforce. Here we see why the derivative of x to the power n is n into x to the power n minus 1 for a polynomial differentiation. We use a binomial expansion to understand this. A delta change in the radial measure of a polynomial system results in a volume change which is given by the binomial expansion. If we ignore the higher order terms with squares and above for the delta, then what we get is n into x to the power n minus 1 as the total change. What we have here is a quadratic rate of change, a uniform growth in the change, which results in a total change that is quadratic. Cumulative sum of uniformly increasing changes is a quadratic change. This is easy to see because, for example, the differences between the consecutive squares of integers is consecutive odd integers. Here the core concept is the way we look at the basic arithmetic operations such as multiplication and addition. Instead of looking at them as binary operations with the two inputs, we can consider them as a transformation defined by an operation, which is applied on a single input to produce an output. Here, the transformation operator is not really the multiplication symbol, but it is the symbol and one of the multiplicand acting as the operator. You will see why from the diagrams. The operator represents the expansion of the input space as seen on the left, or some mapping as seen on the right. And there is only one input to this operation. The linear operator concept can be extended to two dimensions, where we transform a vector, which is a 2D number, kind of, using a matrix operator. This can be seen as a combination of two 2D numbers as operators, which act on the vector and its a mirror reflection. The two operators are applied on the vector and its reflection, respectively, and the results are summed up to arrive at the final result. And finally, it is possible to look at exponentiation as a linear transformation when we change the coordinate system to lean log scale. Then the base of the exponentiation or the base of the logarithm becomes the operator. This can also be applied to a polynomial change to convert it into a linear change as well by changing the scale for one of the axes appropriately. That is all, folks. Thanks for watching.